All right, so I want you to, we went through section 1.2 yesterday, or day before, maybe I guess it was. Last Friday, we introduced that a little bit. Very introductory stuff, just kind of getting you used to the concept of geometry. Now we're going to start to get a little more specific. I'm going to, just so you know what the schedule is for the rest of the week. We're going to cover this stuff today. I'll cover something different on Friday. Tomorrow will be a lab day. So tomorrow is a day where you could, if you wanted to, you could retake the algebra review test if you want to. You could work on assignments if you're done with that. I'll have this assignment will be up today. In fact, it's already up. So you can be working on that tomorrow in the lab if you want to. Just keep in mind that the algebra review test, the algebra review assessment, does go on grades as of tomorrow. Now, you have all semester to improve that grade, but it is going to be activated tomorrow. So just be prepared for that. So you may, if you haven't done it or you need to redo it, tomorrow might be a good day to do that. Okay, so we're going to look at some more specific stuff. Before we jump into this, we're going to do a little thought experiment. I want you to think about something. And this is going to illustrate, I think, is an important point. So imagine that you have two cans of soup, two identical cans of soup, and you're going to put them on their sides. So you're going to lay them down, like this, at the top of a ramp. The ramp is divided into two parts. On, let's say, the right-hand side of the ramp, it's a highly polished metal surface, so very slippery. It's sprayed with like a Teflon spray, so it's really, really slippery. The other side is covered in it's covered in rubber, let's say, kind of just a little bit bumpy rubber, so it's sticky, right? So it's got some friction. Are the two soup cans going to proceed down the ramp in exactly the same way, or is there going to be a difference, do you think? There's going to be a difference. Alex, what do you think is going to be the difference, Alex? When I put the one on the right side that's very slippery, what do you expect it's going to do, maybe? Okay, it might slide. It might slip down, right? Because it's really slippery. What about the can you put on the rough side? What do you think? It might roll, right? So there's going to be a difference there. Just speculate for me, and we're not going to get to the bottom of this today, but I want you to just speculate for me. Which one do you think is going to get to the bottom of the ramp first? What do you think? The one that's on the really slippery surface, or the one that's on the stickier, rougher surface? Which one? More slippery. Does that make sense? It's probably going to get to the bottom quicker. Let's say when they get to the bottom, they roll down without, they just roll down so they're perfectly aligned. When they get to the bottom, they hit a flat surface with, let's say the bottom is all, well, okay, let's say it continues slippery on the right and it continues with the rougher surface on the left. They get to the bottom. So then they're going to move along the flat horizontal piece for a while. Which one do you think is going to end up going further, maybe? Slippery one? Maybe. It's possible that it might even be the other one, though. Even though it goes slower, it might be the other one. But regardless, would you say there's a difference in the motion? For sure, there's a big difference. The big difference has to do with whether it slips or rolls. Okay? This is a physics question. Hopefully you'll all take physics in the future. I hope to see you all in the physics class. Physics deals with problems like this. Physics just explores the way the universe works, answers problems like that, and other problems too. But I mean, if you really are interested in knowing how soup cans are going to get down an incline, physics would be what you'd want to appeal to. That might give you some insight. The big difference here is that it's the rolling motion. The can that's rolling down the incline, it's not going as fast linearly. It's not going from point A to point B, from the top to the bottom, quite as fast. But while it's doing that, it's picking up some rolling speed. There's really two kinds of motion that are important in physics, and we're real familiar with one of them. One kind of motion in physics is going to be the motion from point A to point B. We can discuss that, and already, without having studied any physics, you're already pretty good at that. You could talk about what's the distance between the 2 points, or the displacement, we might call it in physics. How far is the object moving from point A to point B? We could measure that, and you could tell me, you could discuss that. We could even talk about maybe how fast it's going. You're used to talking about speed, or in physics we might prefer to use velocity, but you're used to these terms. You're even used to the term acceleration, right? It starts slow and it ends up fast, so it's accelerated. All that stuff we could talk about right now, and you'd be fine. But the part you wouldn't be maybe as proficient with, you would be as comfortable with, would be the rolling part of this, right? As the can on the sticky side rolls down the incline, it's picking up a bunch of rolling speed, and it's actually undergoing some angular displacement. It's turning through a big angle many times around the can. If you look down the axis of the can, it's spinning around. It's picking up angular speed. The speed at which it rotates in physics we talk about as being angular velocity, and it's even picking up some angular acceleration. As gravity pushes on this thing down the incline, it's turning it. It's causing what we call a torque. You might have heard that word before, and it's making this thing spin faster and faster. And it's actually storing energy in the can. If we got to the bottom, and let's say I had I don't know, what would this be, like 2 nails or something. I'm just going to poke into the side of the can and pick it up. The one that's been sliding is not really going to be rolling very much. I'm just going to pick it up and it's going to look the same. But if I hit the other can, the one that's rolling, and I grab it and pick it up by the nails, it's going to continue to roll maybe, right? Does that make sense? If I put it back down again, what's it going to do? It's going to take off because it's got that rolling energy. Does that make sense? If something's rolling and I put it down, it's going to kind of grab the surface and go. So we've actually stored some energy in that can, right? Why am I talking about all this? The point I want to make is that there's a difference. There's a difference. Understanding the angular part of that is a little bit trickier, but it's still important. It's still an important part of motion in the world is the angular part, right? We're not very well equipped to talk about that because we haven't really talked about angles very much, because it all has to do with angles. And even though, you know, you'll go a lot further with this in math and in physics if you choose to go that route, geometry is where we first kind of start to get a glimpse of studying the angular part of this. And it's new stuff. We haven't talked about it very much. But what I want you to think about as we go through, you know, this chapter and beyond, I want you to kind of draw a parallel between the relationships that we find among distances, and we're going to talk about that today. Today we're going to talk about segments, which are, you know, point A to point B kinds of things. We're going to talk about how to calculate distance and some stuff like that. It's going to be probably a lot of its review. But on Friday, we're going to have a similar discussion, but not about segments and distances. It's going to be about angles. But what I want you to see is that all of the relationships that we develop today, we're going to see again in a slightly different context with angles on Friday. The stuff we do in linear land is exactly parallel by the stuff we would do in Anglevania. They're 2 different places. One of them deals with distances and straight lines, and one of them deals with rotations and angles and things, right? But the relationships are very, very similar. And if you see it in that way, it makes both of them a lot easier to understand. Okay? Hold that thought, I'll come back to it. But I just want you to be thinking in that way as we talk about this stuff. Okay, so moving on. Segments and their measures. We talked about some of this stuff the other day. I can't remember if I mentioned this or not, but I'll just briefly just give you a little vocabulary. Not a big deal. We talked earlier about definitions, right, and terms, and we had some defined terms, and we even had some things like points, lines, and planes that were so basic we couldn't even define them. We just understood what they were. We called them undefined terms. In geometry, in addition to having definitions, we also deal with a lot of rules. And in math in general, but in geometry especially, we use rules to try to understand the relationship between geometric things. These rules, some of these rules we call postulates or axioms. Those are rules that are so basic that we don't have to prove them. We just know they just make sense. Some of the rules are a little more complicated, and those are called theorems. Theorems are things that we have to actually prove first before we know that they work. And once we've proved that they work mathematically, then that's a rule that we can continue to use, right? We're going to start off today, we're going to look at just really 1 or 2 examples of some postulates, some really, really basic rules that we just know have to be right. We don't even have to prove them. Okay, here's one of them. And this might even seem kind of silly in a way. The ruler postulate just says that if I have 2 points, A and B, I could measure a distance between them. That's really all it says. You know, we could define, if I want to know how far apart they are, I could measure a distance. I might measure it in inches, I might measure it in centimeters, I might measure it in, you know, meters, whatever. But I could put a ruler up there or a measuring tape and measure a distance. So distance is a thing that makes sense to us. That's really all it's saying. Okay. I need to mention one thing about this. how would I write this, go away. How would I write this thing up here? There's an arrow at the other end. I wish this thing would go away so you can see it, but there's an arrow at both ends of this. How would I write that geometric thing? If it's going through points A and B, how do I write that? What's the symbol? What is it, first of all? It's a line. How do I write line AB? Okay, so I'm going to write A and B because those are the points on the line. And then above that, I'm going to add the symbol for line, which has arrows at both ends, right? Okay, we're familiar with that. What about if I want to do just this part? What if I just want to do, I just do this part, say from there to there, if that's all I'm including. What is that?
Segment.
That's a segment, right? Segment AB, and how do I write the symbol for segment AB?
AB.
Okay, now I've just got a segment over the top, no arrows, right? What if I want to do, let's say I want to continue this off in one direction, so I want to do that. Starts at B and goes forever through A.
AB. Ray.
Okay, it's a ray. So what do I write? Oh, it's got to start with B, don't I? Because the ray, the initial point is B. It starts at B and it targets A and goes forever in that direction, right? So there is an order that's important here. It didn't matter with the line or the segment. The order was irrelevant because if I switched the points, it didn't really change around what that was. It was just a segment that goes from A to B. But the ray, it's important. The ray starts at B and targets A, so it has to be in that order, right? Okay. Well, those are all geometric things that I can draw, and so they need symbols. If I want to talk about a distance between points, that is not a geometric thing. That's just a number, right? We call that a measure in geometry because it can be written as just a number. So if I want to discuss just the distance between A and B, I write it like that. I just write it as AB with no symbol on top. And that's what we interpret in geometry to mean the number value that goes with that distance. So that's the distance between A and B, or we could also call it, if we wanted to, maybe the length of segment AB. Same thing, right? You can interpret it either way. But if there's no symbol, it's a distance, okay? Okay, so moving on. And in Moodle, we would just write that as just as AB, right? With no, we wouldn't write line or ray, just AB. Okay, we can skip this. Okay, this is important though. We talked about this yesterday, and this is a big deal. And I want to use this for two reasons. I want to talk about between, what between means in geometry. We'll review that because it's important to understand for geometry. But I also want you to see that this illustrates the way mathematicians have to communicate and think. Mathematics is very, very precise. Language is not. Language is an amazing thing. If you look at the way our brain is constructed, there are parts of our brain that do certain specific tasks. Like the frontal lobe is what you use for logic and thinking. There are parts in your brain that are responsible for interpreting vision. There's a huge part on the side of your brain, on both sides, really large part of your brain, a disproportionately large part. It doesn't seem like it should be this big. That does nothing but interprets language, communication. We are built, we're social animals, we're very social animals. We need to communicate. It's important for us to be able to communicate. In the past, it was important for us to survive, and now it's important for us to be able to transmit information and emotions, and we have a really rich way of communicating non-mathematically. If I say, nice job on the test, I could mean, nice job, but I could also mean like, nice job on the test. I mean, you just did terrible, right? I mean, there's just the words are the same, but the way I said it imparts a whole different meaning, and our brain just latches onto that stuff and really derives a lot of meaning from it. It's great because it allows us to do things like be funny or be sarcastic or be serious just by the tone of our voice, but in math, we don't want any of that stuff. In math, we want the message to be very clear and precise, and no matter who's saying it or in what tone of voice they're saying it, it's got to mean the same thing, right? So in math, it's not as interesting, it's not as rich, it's not as, it's a different kind of communication, but it's meant to be very unambiguous and precise. So when we talk about being between, this is a good example. In mathematics, we've got to say, okay, what exactly does it mean to be between? And we have to write that down as a rule that we can apply. So it's like a contract, kind of. It's got to be very precise, and there can't be any loopholes. We talked about yesterday maybe a context like this. Is E between D and F?
No.
I mean, not mathematically, but maybe non-mathematically, maybe we could say it is. You know, it's sort of betweenish, right? But in math, in geometry, it is not between. It's not between. E is not between D and F, but B is between A and C, right? What's the difference? Say it again.
It's on the line.
Okay, so for one thing, B is on the line, isn't it? B is on line AC, whereas E is off of line DF. And so for that reason, E is disqualified. So that's one criterion that's important for us. When we define betweenness, the point that's between has to be on the line that contains the other points, right? So good. So is that all we need, though? What if I continue this line? If I continue the line, and I'm going to put another point up here. Let's just call it point X. Is point X between A and C?
No.
It's not, is it? But it's on the line. So there's got to be something else involved there, right? And that's the part that I can't remember how far we got with this yesterday or the day before. But we did get to the equation. Okay. So what do we say about that? How can we now say, even though they're both on the line, B is between, but X is not? What's the other criterion here that mathematically we can apply that says, yeah, yes and no? Do you remember? Okay, yeah, they either, here's what we have to be able to do. Think of it in terms of an ant walking from point A to point C, right? If the ant walks from point A to point C and takes a pit stop at B, then the distance he travels during the first part of his journey would just be this, wouldn't it? Right? Oh, sorry. No, that's right. Make sense? That represents the distance from A to B. Takes a little pit stop, and then he continues his journey to point C. What's the distance he travels during the second part of his journey? BC. Okay. What's the total distance he travels? AC. If that's true, then B is between A and C. Let's just attach some fake numbers to this. Let's pretend we measured this and we found that the distance from A to B was 3 and the distance from B to C was 6. So if we attach those numbers, we'd get 3 plus 6 equals, how far apart are A and C? 9. And that's true, isn't it? Right? What about X? Let's talk about a different journey. This time the ant's going to start at A, take a pit stop at X, and then travel all the way to C. Let's just pretend that this distance is, how about 2? Okay? So let's try this one then. Is this true? Is AX plus XC equal to AC? Well, what's the difference, the distance from A to X? 2 plus the distance from X to C would be what? Yeah, well, hold it. 9 plus 11, so 11? And we already know that the distance from A to C is 9, right? Well, is that right? Is 2 plus 11 equal to 9? No, it's not. So that tells us that X is not between A and C, right? Because the distance from A to X plus the distance from X to C is not equal to the distance from A to C. Does that make sense? That's a tricky way of expressing a concept. I mean, that math is like it. It's like a puzzle. We got to find a way of saying, okay, it's got to be in the middle somewhere, but saying it's in the middle isn't good enough in math. That's too ambiguous. We got to be able to say it in a way that's mathematical, and that's the way we say it right there. That means, that's our math way, whoops, that's our math, what is this doing? That's our math way of saying B's in the middle, okay? What do we call that? Well, we give it a fancy word. We call it the segment addition postulate, but it's what we just described. So B is between A and C if it's on the line, and AB plus BC equals AC. Okay? Questions on that? Does that make sense? Okay? Do you see my point about how it's a little harder than just saying it's in the middle? In math, we got to break it down to something that's really precise and understandable, right? That we could communicate to anybody studying math any place in the world and they would get it, right? Okay. So that's the segment addition postulate. The other thing I wanted to talk about today is something that, this will be a review. How many of you remember using the distance formula in the past? Just, I don't care if you remember what it is. Did you remember using it ever, calculating the distance between points? I'm sure you did. but you may not even remember it. But I guarantee you did, somewhere in middle school, maybe in high school too, I don't know. The distance formula, how many people remember the distance formula? I don't see a lot of hands, and that's not surprising, because this is another thing that knowing how your brain works is very, very useful. If you know how your brain works, you can take advantage of the way it works to learn stuff better and quicker. Your brain is horrible at memorizing facts. The way your brain actually works, I'll just give you a 5-minute sort of rule, I'll expand on this later. But the way your brain works, there are, did I talk about this at the beginning of the year? No. Okay, there are billions of cells in your brain called neurons. Neurons are the classic brain cells, right? Brain cells are just your, when do you have the most brain cells in your life, do you suppose? Well, actually, they do multiply. Your brain mass doubles from birth to age 5, and then again from age 5 to about now. Right now is about your peak in terms of brain cells, honestly. You're right at about the peak in your life. From here, it's downhill. You bump your head, you kill some brain cells. I mean, things are, they go away. But the good news is that the number of brain cells is almost irrelevant. That's really not the part that makes you smart. There are some other cells in your brain called dendrites and axons, and they do this. Well, this is really interesting. I want to show this to you. What did I give all this? So they look like this. In your brain, like if this is a neuron, they're not really purple, but this is a neuron, and here's another neuron, and there's another neuron. There are cells that string out throughout your brain, axons and dendrites. They're like little tentacles. So they go out like this, and that would be an axon, and then a dendrite coming from another cell, brain cell, would come up here, and they sort of meet. There's a real narrow gap there that chemical transmitters, send electrical signals across these gaps. But the main thing is they connect the brain cells. That's really all I want to tell you, is they connect the brain cells. What makes you smart is having more of these connections. That's what you can correlate intelligence with, is the interconnectedness of your brain. If you have very sparse connections, then you're not going to be as intelligent as somebody that has a huge amount of these stringy fibers going from their brain cells. When Albert Einstein's brain was cut into thin slices and studied after he died, what people found was his brain was not abnormally large, despite the fact that we all know Einstein was the genius among geniuses, right? But it wasn't abnormally large. What we found is that it was really dense. He had just an extraordinary amount of these axons and dendrites connecting his brain cells. And that's why he got so smart. Now, the good news is, in math, there are certain things you can do in life that really, and some of them are bizarre, certain things you can do that cause your brain to produce more of these, and you literally increase your intelligence. So one of them is athletics. Anytime you have to do something that involves precise movements, like athletics, that recruits these dendrites and axons. And especially if they're really precise movements and things you're not used to. This is going to sound weird, but if you want to get smarter, one thing you can do is, like, one day a week, if you're right-handed, eat with your left hand. Believe it or not, that sounds really bizarre, but think about the kinds of things you can do with your right hand. You can write, you can paint, you can write, you can do, you have a lot of control over your dexterity, and you can write very finely. You know what I'm saying? Try it with your left hand. You can't do it at all. I mean, I would look ridiculous if I tried to write with my left hand up here. But every time you try to do something with your left hand like that, you're trying to write with your left hand or eat with your left hand, you're having to train your brain to do these really fine muscular movements that it's not used to doing. And when it does that, it's rapidly recruiting all these connections between the neurons, which make you smarter. So it sounds really stupid, but that's something you actually could do. Other things that really are effective, well, the thing that's probably the most effective is what you're doing right now, mathematics. Anything that's really abstract, where you have to do a lot of thinking about relationships that aren't concrete, that also makes you a ton smarter. And the good news is you get to use that intelligence for other stuff later in life. Once you establish these connections, you literally become smarter at everything you do. So that's one really good reason why math is an important thing to do. Puzzles, any kind of, like if you're doing crossword puzzles or Sudoku, I mean, those kinds of things also are really good at recruiting these kinds of cells. Reading is good, foreign language, lots of things that are good. Basically, lots of academic things are good. But math is among the best. Why was I saying this? Why did we get off on this tangent? Gosh, I can't remember why I got off on this tangent now. It was important though. What was I saying? I was talking about, help me out here. Where was I when I got off on this bizarre tangent? Einstein's brain, rewind a little further. Where was I? Can't remember. I do this sometimes. Getting smarter, getting smarter. I think I was talking, I can't remember what I was saying. Yeah, okay, that's a good idea. I was talking about, oh, I know what it was. I got it. Yeah, it was formulas. Yeah. Formulas don't use a lot of these. Formulas, when you try to memorize things like state capitals. How many state capitals do you know, Nick? How many? Do you know most of them? Who knows? Does anybody know all the state capitals? Probably. There's probably someone in here that does. I did at one point in my life. God, I bet I could get about 20 of them. I don't know any of them. I mean, when do I ever use that stuff, right? So I don't really know my state capitals. When I learned my state capitals back in 1492, it was so when I learned them, I mean, it was not high level learning. Your brain does not attach strongly to facts. Facts are just like individual neurons that are weakly connected to other neurons. It goes away in a hurry. Those get gobbled up and used for other more important things. So don't try to memorize facts. I will, and you can call me out on this, I will rarely ask you to memorize stuff. I would much rather that you know how to use stuff and just look it up. I mean, now we just Google stuff. If you want to know what the Pythagorean theorem is, just Google it. But what I want you to know is how to use it. Concepts and processes are more complicated, and they're like athletics or like riding a bike or something. Once you know how to do it, you really can always get it back pretty quickly because it's a complicated thing. There's lots of interconnectedness in the brain that is responsible for knowing how to ski, right? So even though I haven't skied in 10 years, I guarantee I could go back up and I'd be okay. I could ski okay, right? But I don't remember my state capitals because that's not a very strong connection. So what I want you to challenge yourself to do, especially in math, is don't memorize stuff. Just try to understand how things work instead. Here's a prime example, the distance formula. I hate the distance formula because it's a formula. It's just something you're going to forget. I'm going to tell you anyway, but then I'm going to show you a better way. So here's the distance formula. If we got the xy plane, and let's say we want to find the distance between 2 points. I'm going to pick a point that's over here at -3, +2. Those are the coordinates, x and y coordinates, right? We got another point over here at 4, 5. So over 4 and up 5, let's say. We want to find the distance between those points. Same thing as saying the length of that segment. Do you remember how to do that? Vaguely. I'll write the formula. Do you think you remember anybody? It's a triangle. That's the way I want you to remember. It's a triangle thing. That's a better way to remember it. But here's the formula. Here's the distance formula that you have seen and promptly forgotten. Distance formula says that the distance is the square root of the quantity x2 minus x1 squared. Remember this?
Yeah.
Plus the quantity y1 plus y2 squared. Well, it's no wonder you forgot that. Look at it. It's
Good morning, Buckaroos. Can I please have your attention for a quick announcement? We will be serving lunch in the cafeteria starting at approximately 11:16. There is some testing that is still going on. Please do not enter the cafeteria, the commons area, until 11:15 for lunch. Thank you.
Okay, can we get that? Okay. So that's the distance formula. What in the world are the x1s and x2s and y? What does that even mean? What are those things? What's x1, y1? Okay, they're coordinates. And when you see subscripts like this in math, like the numbers down below it, up above it's an exponent. But if it's down below, all that's doing is it's just an index. It's just telling us, okay, we've got 2 points up there, and one of them we're going to call 1, and one of them we're going to call 2, right? So what that means is, if I were to just come up with some general points, like let's say we've got a point here, we're going to call this point 1. So its coordinates are x1 and y1. And we've got some other point over here, which we're going to call point 2. So we attach a 2 to the x and y value. values, x2 and y2, or really we should say x sub 2 and y sub 2, but you get the idea. And so then if I want to know the distance, I'm just going to take these values and plug them into that formula, okay? So we could do that, and it works, and if you want to, I'm not going to say you can't, but there's a better way to think about this. How many people know the Pythagorean theorem? I bet you, you're being bashful, but I bet you almost everybody knows the Pythagorean theorem, really. You've talked about it, maybe not a lot. Finish it for me, though. A squared plus b squared equals?
C squared.
We all know, right? Anybody on a game show knows the Pythagorean theorem, but they probably don't know the distance formula, right? Pythagorean theorem is easy, though. Pythagorean theorem just says if we have a right triangle and the legs have lengths a and b and the hypotenuse is c, then we know that c squared equals a squared plus b squared. I want you to notice something here. If an ant is walking from this point to this point, sure, he can walk at an angle in a straight line, but what if he's only going to walk horizontally and vertically? So first, let's say he walks horizontally. So he walks over in this direction a certain distance, and then he walks vertically to that point. What did I just create? I created a right triangle, didn't I? Okay, the distance up here is really just the hypotenuse of that triangle, isn't it? What is the horizontal leg? How long is it here? How far is the ant walking horizontally? 7. How'd you get that? Okay, because I have to go from this x value to that x value, right? And from -3 to 4 is a distance of 7. Agreed? Okay. Here's what we can call that. The horizontal leg, let's just call it delta x. And all delta means in math is change in. So it's change in x. We just need to know how far apart are the x values and how far apart are the y coordinates. And all we've got here then is just a Pythagorean theorem relationship, which is simple, right? We don't even have to worry about keeping track of which point is number 1 and which point is number 2, because we just need to know a distance, right? So here's my suggestion. If you want to know how far apart -3 and +4 are, for example, always subtract the smaller value from the bigger value. And then your answer always comes up positive, and it's easier to deal with. Here's the problem you can have if your answer is negative. Who's got a calculator handy? Anybody got a TI 80 something handy? Somebody? Anybody? Bueller? Abby's got one. Okay, try this. You're gonna be my guinea pig. So try what is negative, put this in your calculator, -7 squared. What's she gonna get? Anybody know?
49.
No, she's not gonna get 49. You got what?
Negative.
-49. Is that right? Okay, it is right, but it's not what we meant to do. This is important for you to know about with the calculators. The calculators are smart enough that they follow order of operations. So what's the order of operations here? Well, the negative sign is really a -1 that's being multiplied by this stuff, right? That's really what a negative sign does. So what I have to do first by order of operations is square the 7 and then multiply the negative sign. That's not what we wanted to do, though. What do I have to do if I want to get the proper answer, which is up for -7 squared, which is +49? What do I have to do? Anybody know? Well, I could, but if I want to use the squared, I have to put parentheses around it. I have to put parentheses around the -7. Now try it. 49. So it works. But that's something you could forget to do, right? Everybody, I forget that sometimes. So you might forget to put parentheses around a negative number. So do you see the value of, and we're going to have to square this in the Pythagorean theorem, you'll see in a second. So do you see the value of always making delta x and delta y positive? You avoid some errors that way, right? It's easy to do. You just subtract the smaller x value from the bigger x value and the smaller y value from the bigger y value. So delta x in this case, I've got to clean this up a little bit. So delta x is what then? Oops. Delta x is the bigger x value, which is 4, right? Minus the smaller x value, which is -3. Subtracting a negative is the same as what? Adding. So 4 minus -3 is 7. Good. Delta y. What's the bigger of the two y values, 2 or 5? 5. So it's gonna be 5 minus 2, which is 3. Okay, so now all we have to do is the Pythagorean theorem. Instead of the distance formula, look what we can do. We can trade that whole messy distance formula for this, right? D squared, that's the distance squared, equals delta x squared plus delta y squared, because aren't those the legs of the right triangle we created? And if we want to actually solve for D, how do I undo squaring it? Square root it, right? So then we just end up with D equals the square root of delta x squared plus delta y squared. Now I ask you, does that look better than that? A lot better, doesn't it? See why that's a much better way to do it? So what do we end up with then? Well, we get the distance equals the square root of 7 squared plus 3 squared. That's pretty easy, right? What is that? What's 7 squared? 49 plus 3 squared. So what? The square root of 58, right? That's the answer. That's an exact answer. Now, I might ask you to simplify that, but this one can't be simplified. And that's the stuff we worked on early in the year, finding a perfect square that divides into 58 and simplifying it. But half the time, I'm just going to ask you for a decimal approximation anyway, which makes it easy. You just plug the square root of 58 in your calculator and round it to a decimal, right? Does that make sense? Okay, we're out of time. I'll maybe go through 2 examples at the beginning of class tomorrow to make sure we got it, and then we'll go to the lab.